Okay, so in the chat box, I wrote my email address. Okay, and you have to submit the solutions of the assignments in this email address. So you have to write the solutions, then you have to take a picture of it. Okay, one by one. I mean, question by question, like from first question, second question, and so on. And then you have to upload it and send it to me. Okay, in that email ID. And please send it through your official email ID. Okay, so that I can recognize who is sending. Yeah. You have any other question about anything?
Sir, in variable length coding, we will get only one problem taking more time, or we will get more problem.
What do you mean? I didn't understand your question. Can you please repeat it?
Sir, you said there are two schemes in coding: fixed length and second is variable length. Okay,
Mm-hmm.
and you also said in variable length we face some problem like taking time. Okay, so you mentioned only one thing: it will go to taking more time. My question is, there is only one effect, or it will variable length may be affected by other factors?
No, it can be for other factors as well. For example, if we have to use, let's say, use cost of the channel is also involved, right? If you use a channel many more times, okay, then cost is also involved. Let's say you have a channel where you can send, let's say, 4 bits, okay, per second. But suppose you have a coding scheme where for a particular source letter you have 5 bits, okay, and then so you have to use the channel twice. So cost is also involved. So that also can be explained like that way in order to minimize the cost. But these are all ad hoc things. I mean, these are all very technological things. It's technological in a sense, like for the implementation. But these could be problems. But these are not our problems to address. But these could be, let's say, the problems. Our concern is to develop the mathematical theory. But this could be. I mean, these are the things one has to also should. I mean, one has to also discuss like what will happen if I do a variable length coding. What is the advantage? What are the disadvantages? So this kind of things, like yeah. And now the thing is like, how to address this issue. Let's say, okay, like suppose that I want to use variable length coding. Okay. Now the question is when I'm developing a technology to do this. Okay, how much so theoretically speaking, we can always say it is the cost of the time, cost or time or waiting time. But the thing is, when somebody is developing the technological details of it, okay, developing a technology to demonstrate it, then so that is a technological challenge how to overcome it also. Okay, so if there is a way to overcome it, or let's say waiting time is not a big issue, let's say, but that is a problem for the developer, so not for us. Our thing is to address what are the advantages and disadvantages with all the schemes or whatever the theory we're talking about. And then it is a job of a developer to overcome those issues. Yeah.
Sir, by which way do we need to submit the assignment?
Did you download it? Did you read it?
Yes, sir, I downloaded it, but you couldn't read.
Huh? Did you read it? Or did you download it? I could not
Yes,
hear you.
I've seen it. I've seen it. Okay, fine.
Yeah. Okay. So yeah, anything else? Okay, then I think I can start. Okay, so yeah, as we are discussing, so we're talking about source coding. Okay, so we have some source letters, let's say, or alphabets. Okay, which you want to encode using some other alphabets, let's say. Okay, or maybe we have some letters, whatever it is. We have some symbols also, you can say, let's say. So in our model, we always assume that we have some letters that we want to encode using some kind of other alphabets or symbols. For example, if you want to encode it as a binary sequence, then our alphabet is only 0 and 1. Okay, and then the question is, so D is, let's say, the set which is just 0 and 1, and we say, let's say we have some symbol like A1, A2, AK. So our messages, whatever we want to send, they are all made of sequences of symbols from this set. Let's say this set is some X, or let's say this is some A, whatever it is. Okay. Now, so we want to send a sequence of these letters A1 or symbols A1, A2, AK of some particular length. It could be of length some L or something. Okay. And then the job is to is to decide what should be the encoding scheme. That means, so suppose in the channel, we cannot directly send the symbols because the channel does not understand the symbols, say 182AK. Then our job will be to encode these numbers or the symbols A2, A182AK using these alphabets like 01 here. So if we use the alphabet 01, then we say this is a string of 01s or just encoding these symbols using binary strings or binary sequences. Okay. Now we said also there are two kinds of, let's say this is what is called, let us assume that this is what is called source coding. Because of why? Because source, the information source only generates this sequence of, let's say, symbols. Okay, and we want to encode that. Okay, so if you remember the picture last day we had, we said yeah, this was the picture. Here we had source, and then we have source encoder, and then we have channel encoder. So there are two things. One is channel coding, one is source coding. Okay, so we are right now we are talking about source coding. That means once once, let's say, a sequence of symbols, say 182 is generated, then how to convert it into strings of 0 1s. And once you want to do that, so first thing will be how to decide about the string of 01 corresponding to each of these symbols like A1, A2, AK. Okay. And then we said there could be two schemes. One is which you called the fixed length coding or fixed length code words. Okay. Fixed length code words for each, for AIs, for each I, or it could be a variable length. Variable length. Okay. Variable length code words. And then the question is, there are two questions here. Okay. We talked about, okay, so variable length could be a problematic thing because of a phenomenon like waiting time or the cost of the channel you want to use. Okay. But fixed length channel, a fixed length code was do not have these problems. Okay. But then the question here is, okay, we also have seen that variable length code words also relates to the idea of entropy in some sense. We just gave an example, we discussed an example, but we'll focus on this later on also. I mean, we'll try to prove that, okay, what should be so the length of each of these code words, okay, how to take advantage of the probability distribution of all the symbols, okay. But we will discuss that, okay. But before, So we just gave an example and we have seen that, okay, this has to be the entropy, the expected length of the coding scheme. If you use variable length, it has to be the entropy of the random variable involved with all these symbols. Okay. Now, so the question is for the source coding, a bigger fundamental question for the, let's say, the fixed length code. Okay. So let's say, let us talk about fixed length. Okay. Suppose we are talking about fixed length code words. And here, then the question is how to decide this, how to decide the length. Suppose we are talking about fixed length. That means length of, okay, each code word is same. Okay. So code word corresponding to each of the symbols or letters, let's say 1 A to AK. Okay. They're same. The question is, if this length is fixed, how to decide that? Okay. What should be the length? Okay. How to decide the length? This is a bigger question. Okay. So even if we decide that, okay, we'll generate fixed length code words, okay, and fixed length code words have actually practical applications in a sense. The first, okay, we'll talk about that a little later. But let us say, first of all, the question would be how to decide the length, the fixed length. Like each code word has this particular length. Okay. And note that for the communication, okay, we also said one interesting fact is that once we encode all these letters, okay, and we send it to the receiver should also be able to decode it. So the receiver should create the original message, let's say, or original sequence of letters, okay, from the sequence of 0 ones. Okay. So that means it is desirable that with high probability receivers would be able to do that. And one ad hoc way of or informal way of doing it is that doing it or guarantee it is that each code word, okay, is different. Okay. So for each different for different symbols, you have different code words. Okay, then at least it is uniquely decoded. So that there's a sufficient condition. Okay, that it will always give you different code words if you send different sequence of letters. Okay. In a probabilistic sense, we always have to ask this question: what is the probability that there is no error? Okay, there is no error means there is enough sequences of 0 ones, okay, which can represent the sequence of letters, okay, sequence of source letters or source symbols like A1, A2, AK. Okay, yeah. So now we'll try to find out now. Actually, we'll determine what should be the length of this. Okay, so what should be the length of each of this code word? Okay, if we want to use fixed length code word, and there is a theorem for that, which is proved by Shannon, which is known as a source coding theorem. But we will not discuss. We will not state, let's say, the theorem first. We'll develop the proof of the theorem, and finally we'll state the theorem that this is what we have proved. Okay, this is how we'll go about it. Okay, so here is the setup. So let us say we have a sequence, okay, which you want to send, that the sender wants to send a sequence of letters. Okay, so let's say assume that the sender wants to send a, let's say, finite sequence. So everything is finite, let's say a finite sequence of letters or source letters. So of source letter. Okay, and let us assume that a prototype like UL, let's say, let us write a sequence, or let us write a bar here, and let us say this is the sequence, which is like U1, U2, dot some UL. Okay, so length L. Okay, so this is the sequence of L letters. Okay, so that the sender wants to send. Okay, now so each of these letters, like UI, let's say, these are from this A1, A2, AK. Okay. Now the first question is, okay, if the sender wants to send a sequence of L letters, source letters, then how many ways the sender can generate such a sequence? How many possible ways the sender can generate such a sequence? Okay, so obviously the answer is, so there could be how many? There are each UI each UI has k many possibilities, and there are L many UIs. So what should be the total number of possible sequence of source letters of length L?
So k raised to the power L.
Yes, so there are k raised to the power L, because this is, yeah. So I'll not classify why it is, because you are postgraduate students, I most of you. So there are k to the power L different sequences. Okay. So this is a question, by the way. I'm not writing the question, so I'm just writing the answer. So there are k to the power L different sequences, sequences of source letters. Okay. Now let us assume. Okay. So this is for the sender perspective. Now let us talk about from the coding's perspective. So let us assume or suppose, okay, suppose each source letter is coded or encoded using alphabets from a set D. Okay, so set, or let's say you can say, instead of, in order to minimize notations, let's say set with uh, uh, using alphabets from a set with T elements. Okay, and each code word has length, let's say n. Okay, for example, this D is 2. Okay, if D is I mean this corresponding set is just 0 and 1. Okay, so this D is just 2 because there are only two alphabets, 0 and 1. So, and each code word, let's say, has length n. Then my question is, how many code words? Okay, how many code words can be generated using this particular setup, that each code word is of length n, and this code word, the letters of each of this code word, okay, come from the set which has D elements. So how many such code words possible? And the number of code words is what? Is the number of possible code words?
D power n.
D power n, yeah. D power n. Okay. Now, what is our basic assumption? Our basic assumption is from the receiver side. Receiver should able to decode each of this code word. So that means it is desirable that which one should be bigger, d to the power n or k to the power l? Which one should be bigger? What is desirable? If d to the power n is less than k to the power l, that means what will happen? There may be more than one messages, okay, which will have same code words, because number of code words is less than number of messages, okay. So one has to have, that is desirable, that k to the power l is less than or equal to d to the power n. So we have to choose n in such a way. So let us first decide our setup. Our setup is the sender wants to send a sequence of source letters, okay, of length L. Question is, what should be, and let's say also assumption is that each code word has same length. Then the question is, what should be the length of each code word? Okay, that is the question we are trying to answer. So now here we assume that, okay, let us say if D is the number of alphabets which are used to encode each of the, so here, for example, you can assume D equal to 2, by the way. Okay, no problem. I mean, I'm proving it in general, so that's why I'm writing in general. Sometimes what happens is if you prove it in general, you can also see the bigger picture. Okay. So so if D is the number of alphabets, okay, using which you want to design the code words, okay, then 2 to the power n is the number of such possible code words, and k to the power l is the number of such sequences, okay, sequence of source letters. So in order to decode perfectly, or in order to have a separate code word for each of this sequence of source letters, we must have this k to the power l is less than or equal to d to the power n. But if this happens, what does it mean? If this happens, then L log of k, here everything will, let's say we will talk about log 2. You can, sometimes they can also take a general log like log base 10 or whatever it is, but in general we'll always consider log 2 because we ultimately want to relate it to the concept of information like the entropy, self-information, and so many things. And this has to be then less equal to n log d. So this implies n by L has to be bigger equal to log k by log d, which is, you can say it is a constant because it does not depend on n and L. Okay, it's a constant. So even if L equal to 1, you can see that n has to be log k, n has to be bigger equal to log k by log d. Okay. So that means, first of all, for the fixed length codes, okay, we need at least, so what is the implication here? Okay, what does it imply? So imply for each, so let's say this imply what? This implies each code word, okay. So we need log k.
Sir, yeah, D should be greater than 2, greater than equal to 2.
Yeah,
Because
yeah, yeah,
cardinality.
yeah, d is greater than 2, yes. Yeah, yeah, greater equal to 2, yeah. So log k by log d, see why we are not taking d equal to 1? Because if we take just d equal to 1, then what will happen? If the length is fixed, that means for each source letter, we have the same sequence. Okay, let's say d is only 0. Okay, we want to encode each of the source letter by some sequence of zeros. Okay, but the length is fixed. So then for every source letter, there is only one encoding, which is not a good encoding, because if somebody sends that, okay, the receiver would not understand what is received, okay, what is the message, so you would not be able to, let's say, decode it. So this implies log k by log d, this many code, so many code letters, or how do I say, code alphabets are required, okay, per parse or for each source letter, okay, for each source letter. Okay, I mean, I can give you an example here. You can type it in Wikipedia and check. So the first, there is something called teletype or telegraph, which I talked about before also, I think. Teletype, so which is a electromechanical communication systems, which people used to use around 1830, 40. Okay, so in the teleprinter, okay, so they use, I think this, so they use, I think they use, I think, Morse code or something, or maybe they use no, not the Morse code, but they used to use uh, code, okay, code words for each of these letters and numbers, and each code word has the same length, and length was some 32 or something like that. So you can get information. You can just type it in teletype or teleprinter. Okay, you can also see some pictures of these things. Very old teleprinter. Okay, yeah. So this is an example of such a thing. Anyway, so yeah. Now, okay. Now the question is, what will happen if we use fewer than this many alphabets per source letter? What would happen? Any idea? So this comes from this, that k to the power L is equal to d to the power n. From here we get this. But what will happen if I take uh, less than this? Mhm. So if you want to relax, then what will happen? If we want to relax this condition, then there is a chance of error, right? There is a chance of error means there may be two different sequence of coded uh, alphabets, okay, or sequence of code alphabets. Okay, code alphabets means whatever the elements are in D. Okay, using which you are, those are the code alphabets using which you are encoding your source letters. So for different, I mean, for you may get, let's say, there is a situation of confusion. I mean, you will not be able to decode exactly. So you will not have two different separate code words for separate messages, let's say. So that is the problem you will have if you want to relax this condition, right? If you want to relax this, then what will happen? Then there will be situations, let's say, situations, okay, such that they we will not be able to, we would not be able to able to, let's say, decode, okay, decode, okay, decode the original message, let's say, or original sequence of source letters from the received sequence or from the encoded sequence or for the uh, code sequence, whatever it is. Okay. So this is the thing. So now what we'll do is, any question up to here? No. Okay. Now what we'll do is we'll try to show that we do not need to assign code words to all possible sequences of source letters of a fixed length like L here. In fact, it is enough to assign code words for a particular subset of sequences of source letters of length L. And if we make this L large enough, sufficiently large, let's say L is very, very large, then we can have a very higher probability that there will be no error and the number of code letters per source symbol or per source letter will be almost equal to the entropy of the random variable x. Random variable x, what is the random variable which involves with a1, a2, ak. So whenever I'm writing this, there is already one pak, pa1, pa2, and pak. So let me repeat it again. So what we're trying to say here is now, suppose we consider all possible sequences of length L, okay? And this is a sequence of source letters. So EY is one of these A1, A2, AK. Now, what we have observed here is, this is what is required, meaning for each, so these many code alphabets are required for each source letter. Okay, if we follow the principle, the number of code words has to be of a particular length, let's say n. Okay, this has to be bigger equal to the number of sequences of length L. Okay, this is the case. But what we are trying to say now, okay, even if we want to send, let's say, U1 to UL, we would uh, not consider all possible sequences of source letters of length L. Instead, we'll only consider a particular subset, okay, particular subset of sequences of source letters of length L, and then we'll show that if this L, this length A is sufficiently large, then the probability of error, that means deriving the encoded sequence, deriving, let's say, decoding the original message from the coded sequence, okay, is less. Okay, there is, the error is less, and not only that, this can be done, that error is less with number of code letters per source letter is approximately equal to the entropy of the random variable here. Okay, this is what we're going to show. And this is what is called the source coding theorem for fixed length code words. Okay, this is what we're going to show now. Now there are two issues here which I will not discuss. I will not discuss in depth. Now, what do we mean by saying So there are two questions here. Let's say, what do you mean by saying n is sufficiently large? What do we mean? We'll prove that mean by saying L is sufficiently large, or L is bigger equal if it's close to infinity. Because if L is close to infinity, then what we actually mean is that the sender wants to send a sequence of source letters, okay, whose length is almost infinity because it is very, very large. Okay. What is the meaning of that? Okay, so the meaning can be considered like this, that you may consider that you have this communication system where this information source is generated, and in the entire lifetime of the system, okay, how many code words are or how many sequence of source letters are sent. Okay, so that length could be very, very high. Okay, so it is, yeah. So what do you mean by saying L is large? Okay, we'll see what is the application of this. We'll come to that. But let's say this is the question we'll keep in mind. Okay. Now what now you'll see here what is the property of log. So somebody said, I think in one of the lectures, that log, the usefulness of log is that it makes or it converts, let's say, multiplication into addition. So this will be used now. Okay. So we already assume last, as we said, that we'll always consider that our channel is memoryless. Okay. Our source is actually not a channel, but since here we're talking about source, so it is a memoryless source. Okay. Assumption. This is the first assumption. Assumption is memoryless, meaning you can tell me. Source is memoryless. What does it mean?
It
It
will
will generate
source.
independent letters.
Yeah, so this, whenever we had picked this, U1, U2, this UL, okay, then U choice of U2, because U1, U2, UL, these are from the source letters, okay, these are one of the source letters. So for example, U1 is one of the source letter, U2 is one of the source letters. So choice of U does not depend on the choice of U1. So these are all statistically independent. So U1, U2, UK, you can consider this as sample of the same random variable. What is the random variable here? Let's say that you denote the random variable. What is the random variable? This random variable means picking a letter from A1, A2, AL. So these are like IIDs. These are like identically distributed independent random variable. Okay. Identically distributed random variable. Independent. Okay. Independent and identically distributed random variables. You can consume like this way. Random variables. Okay. So U1 is independent of U2, U2 is independent of U3, and so on. Okay, there is no dependency between these random variables if you treat them as random variables. Okay, now see what happens if you take this UL, okay, the sequence, okay, of source letters, okay, then what is the probability of this? A particular given sequence. Since these are all independent, what should be the probability? This probability is nothing but these are all, this is a random variable, let's say it's a sequence of random variables, right? X1, X2, let's say Xn, XL here. And they're all independent. So this should be what? Product of
Product of probability of each UI.
yes. So L equal to 1 to let's say capital L. Okay. So given any, okay, let me say, let me give you an example. Okay. So what I mean, let's say we have a source. Suppose we have a source. Okay. Source letters. We have source letters, let's say A1, A2. Okay, this is the source letter. These are the source letters only, A1 and A2. So K equal to 2 here. And also let that some P of A1, which is given, let's say 0.7, P of, let's say, anything you can assume 0.3. Okay. And then you consider a sequence, let's say U something, U3. Okay. And so this is some U1, U2, U3. Let us say, for example, this is A1, A1, A1. Doesn't matter. Or maybe you can take A2, A1, 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 A2, A2. Doesn't matter. This is a sequence. Okay. Then what is the probability of this U3? Okay. This probability of U1, probability of U2. So this is probability of A2 times probability of A1 times probability of A1. So this will be probability A2 is 3 times 0.7 times 0.7, which is something. Okay, which is something. So the thing is, so this is an example. Okay, a very simple example. So for each sequence of source letters or L source letters, okay, we can calculate the probability just by multiplying the probability of each of this. Okay, whatever it is. I mean, you can consider a sequence. For example, if D is just like G1, here instead of A1, A2, you can consider A1 to be equal to 0, A2 to be equal to 1. And once you speak a sequence like 1, 0, 0. So what is the probability? Probability is this one. Okay. Okay. So this is the case. Now, so what do we want to do ultimately? Ultimately, we want to show, don't forget the focus. Okay, don't forget the goal. The goal is to find out two things. What is the value of n? And we said, what is the value of n means what is the length? Okay, this is the n. What is the length that we want to decide? And we said, what should be the length in such that whenever L is large enough, there will be almost no chance of error. Because if there is a chance of error, that is a problematic thing. Okay, if there is a confusion about, or let's say if the receiver cannot decode the received sequence of 0 ones of the received sequence of encoded alphabets, okay, then there is no point, like there is a confusion. So that is not a good coding scheme. So we have to guarantee that. So we have to guarantee like what should be the length n such that the receiver would be able to decode it. Okay. And here we want to show that if L is very, very large, this n, capital N, could be just approximately equal to, we'll say, actually we'll prove what is it, the value. It will be approximately equal to this, what is called the entropy, and the probability of error will be very, very small. In fact, while we are proving this, we said like we will not consider all possible sequence of L, okay, but we'll consider a special set of sequences of L letters, source letters, and we develop our theory, and later we'll show that when L goes to infinity, the theory works. Okay, this is the goal. Now, what is the self-information of UL? I mean, first of all, what we are discussing is what is about this UL bar, okay? What is about this sequence? Let us focus on this sequence so that because we have to use the probability distribution of A1, A2, AK. Here it is, let's say, because EYs are less like A1, A2, AK, they are one of these. So how to use the probability distribution? So we are first emphasizing on the properties of UL bar, then we'll try to use it, okay? So now L bar is a sample point here, let's say some AIs, okay, in sequence. So here we have a joint random variable. So what is the self-information? Self-information. Self-information means what? Okay, we already talked about it, so let us not go back into that again. So what is the self-information of UL? Self-information UL is what? This is denoted by IUL bar, which is what? Which is just log of minus probability of UL bar. Now here you will see the property of log. Log of product of this, let's say UL, L equal to 1 to capital L. And this is what is. So this is a product. Now it will be a summation L equal to 1 to capital L. minus log of P of UL, which is nothing but summation of L equal to 1 to L, which is nothing but I of U of L. So the self-information of the entire sequence, okay, is nothing but the self-information of UL. That means, now see, this is directly, so earlier we said what? Our self-information can also be considered as a random variable, right? And this is very, very important. This is very, very crucial observation here. Okay. Self-information can be considered as a random variable because it is giving some value to a random variable. Okay. So now here what we are saying is the self-information of the sequence is nothing but the sum of the self-information of each of these elements of the sequence. Okay. If that is the case, then what we are saying is we also know that E1, E2, this UL, they are statistically independent. Okay. So this self-information of UL bar, okay, this quantity is the sum of L number of identically distributed uh, independent variables. Okay, this is what it is, random variables. Okay, this is what it is. Now here, if you recall, if that is the case, then we can always recall what is called the weak law of large numbers. Okay, and what is that? So let me just recall what is called the weak law of large numbers, or just the law of large numbers. Okay, so law of large number. Does anybody know what is law of large numbers? I can recall just now. So what happens if you have IID variables? Okay, if you have IID variables, what does this law of large numbers say? Hmm? Okay, let me write it. So here the random variables are nothing but the self-information. Okay, I of this. Okay, then if you go back to the uh, let's say definition, the definition which is given in books. Okay, then it would say that okay, so for independent identically distributed. Okay, this is what is called IID. Okay, I'll not write every time this, but I'll just write IID. Random variables. Random variables. Let's say x1. Okay, x2, xn. Okay, 1 by n, sum of xn or xi, I equal to 1 to n. Okay, this goes to, or this is very close to the expectation of x. X is that variable, okay, which is identical distribution. That means the x distribution of x is equal to distribution of x1, x2, and dot 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 xn. So you can say like x1, x2, xn, they are the samples of x. Okay, that's when n goes to infinity for large values of this. Okay, this is the definition, or this is the statement of law of large numbers. Okay, that way you can see. But here our IID random variables are the self-information. So what can we say about this now if we just apply this? Okay, I am not writing what is the meaning of this when I say this tending to this. I mean, this is a sequence, okay? If you can increase n, right? This is a sequence, or let's say, so if you increase n for each this thing, you will get a sequence. So, and this is converging to EX. So what does it mean? Can anybody tell me what is the meaning of convergence of sequence?
Sir, here
Uh,
convergence will be in term of probability. That means probability of x bar minus mu. Uh,
yeah. Mu means okay, EX. Yeah, go ahead.
yes.
Yeah.
So this sequence will converge in probability sense.
Yeah. So it is all, yeah. Okay. So probability sense means what? Does anybody know?
Sir, in the probability of
Huh.
x, I'm saying the probability of mod of x minus mu
Hmm.
greater than epsilon which is equal to 0.
Okay, so that is enough for me. Okay, if you just, because I as I just told you before, like I'll just recall the statement. I'll not go into the explanation. Okay, if you don't remember it or just forward it, just look at any any standard book on probability statistics. Okay, you'll get it. Okay, so now if we apply this law of large number, because it talks about independent IID random variables. So here we have IID random variables, which are the self informations like I of UIs. So then just applying, so from here, okay, from here, so here, let's say
Sir, can
law
you
of
just say
large
what,
numbers.
sir?
Yes,
Sir, what is X here?
what do you think? What is X here? What could be X? Who can tell me? What is X here?
So X here a random variable, or we can say probability distribution.
Okay, X is the random variable, and x1 the random, so the X is the random variable whose distribution is same as the distribution of the probability distribution of x1, x2, xn. They are like samples of X. So that is the X. So it is IID.
Okay.
So how it is distributed, that is X. The way X is distributed, and x1, x2, xn, they are the copies of X. You can think like that. You got it?
Yes, sir. Yes, sir.
Yeah. So why is that? Why is this issue coming? Because see, how we started with? We started with U1, U2, U1, U2, UL. Okay. This U1 is one of this A1, A2, AK. This U2 is one of this A1, A2, AK. This UL is also one of this A1, A2, AK, because that is our source letters. Okay, that is the collection of our source letters. But U1 is independent of U2. U2 is independent of UL. So the U1 and U2 can be different, but they are independently chosen. So distribution of U1 and distribution U2 are same, but they may take different values. Now, what this theorem is, law of large number is saying that the average value. This is also called the sample mean, by the way. This is also called the sample mean. The left hand side is called the sample mean. It's called a sample because of we are taking n number of samples of X. Okay, this is what it is. That's why it is called a sample. So and this is the mean. So the sample mean always converges to the expectation of the random variable when n is very, very large. So if you take a large number of samples, okay, but this is a mean. Okay, you just first take the each of this x1, x2, xn. Okay, you take the sample, okay, and then do the average. This will be approximately equal to the expected value of X itself. Okay, but x1 and x2 could be different. Okay, yeah. So this is very, very interesting. Okay, so I mean, you can read about this. This is very, very law, and it has a lot of applications. So here we have this thing like I1, I2, IU1, IU2. So if I consider self-information as this, then what is the meaning? Okay, convergence here, this limit also has a meaning. Okay, so the meaning is the following, that for any delta bigger than 0, okay, there exists some epsilon. Okay, so epsilon is a function of two things here, L and D, such that probability of mod of I UL, okay, I will, it's a bar by L minus entropy of U. Okay, I'm just let me first write it and then I'll tell what it is. It's less equal to this. Okay, and delta, it's not D, it's delta. And this goes to 0. L delta limit. L tends to infinity. This is equal to 0. Okay, what it means is the following. So for any delta, okay, that means for any delta positive, okay, for any small delta, there is some epsilon such that this probability is less equal to epsilon delta. Now, what does it mean? This is a difference, okay, first of all. This is a difference. Okay, this difference is bigger than delta, and the probability of this event means what is the probability that this difference will be bigger than any value delta. That means if you pick, let's say delta equal to 0.005, any small number but positive. Okay, because this modulus is always positive, that's why you need delta to be positive, because distance is always positive. I mean non-negative, let's say. So delta is positive. If whatever small you take does not matter, then the probability that this difference will be bigger than delta is very, very small when L is large. Because when L is large, this epsilon L delta, it goes to 0. So that means that probability is bigger equal to 0. That means this is very, very small, arbitrary close to 0. Okay, that means probability of the event that this difference is bigger than arbitrary small number is very, very small, meaning the probability that this value, which is the sample mean here, you see L here is replaced by this capital N as or small n, okay? And some of these xi's are nothing but sum of this IUL, because IUL is equal to L of U1. So these are the random variables here, okay? I of UL, okay? IUL. So x1 here, x1 plus x2 plus dot 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 xn. Here I have IU1 plus IU2 plus dot 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 IUN, okay? And because this is L in numbers, I have to divide it by 1 by L. And expectation here is actually the entropy. Why? Can anybody tell me why the expectation is entropy? Expectation of X? Because AX here is the self-information. So average self-information is the entropy of U. U means what? Like U1, U2, UL, okay? Like here I somehow I denoted as a U. Yeah, here you see U is the random variable, okay? Whose copies are U1, U2, UL, let's say. So it is the average self-information, okay? That means the expected self-information, and that's why it is the entropy. So if we just apply weak law of large numbers, it says when L is large, okay, then the probability that is sample mean, that means I equal bar by L, is always approximately equal to the entropy of U. This is what it says. Any question about this? Okay, no. Okay, now recall that we said will not consider all possible sequences, okay, of length L. So recall that, I mean, we want to achieve more doing less. This is the goal here. So we do not want to consider all sequences of source letters of sequence of, let's say, length L, okay, and these are the sequences of length L of source letters. But we want to have this property that we'll consider only the set of sequences of source letters of length L, okay, which have the property, those sequences which have the property that the difference between this and this, okay, so I mean this is satisfied, let's say. We'll only consider this, okay, and from that, okay, we'll try to say that the probability of error will be very, very small. And from that sequence or that set of sequences, okay, if L is large, we can have probability less than this. And for each source letter, we can have approximately equal to entropy of the variable, random variable, as the number of source letters. Okay, a number of source alphabets for each source letter. and probability of error is almost goes to 0. Okay, so that is very, very close to 0. Is what. So this we do not consider or do not want to consider all sequences, but so what is the sequence or what is the set of sequences that we want to consider? So consider the set of sequences denoted by let's say T, and this has a name. It's called typical sequence. Okay, this has a name, typical sequence. Our typical, and not the sequence, but it's the set, let's say. This is typical set of sequences, in fact. So let us say it's typical set. Okay. Denoted by T, such that or for which, I mean, all those sequences which are in the typical set, which satisfy this above inequality. So, okay, for which, okay, I'm simply saying that I UL bar by L minus H of U, this is less equal to delta, okay, for all UL belongs to T, okay, okay, this is what we want, and this is true for any delta and L, okay. So this is what we want, okay. This is the set of all sequences, let's say, for which this is true. Probability of this is very, very small, okay. Probability of this is very, very small, okay, when L is very, very large. So we only consider those sequences which satisfy that. For any delta, if you give me, so we consider all this. I mean, if you give me L and delta both, L and delta both, L and delta both, then we'll consider set of all sequences, which you call the typical set of sequences which satisfy this. Okay. Now, can you tell me? Okay, so if that is the case, then what will happen? Then see that probability. Okay, so I should use a different note symbol, but let's say probability of T. Okay, guys. So can anybody tell me if T is the typical set, then what is the probability of T? Probability of this event. Okay, so first of all, observe that here probability of this event is less equal to epsilon L delta. Now this symbol you see here, this symbol is bigger equal to. The typical set is defined as less equal to. So what should be the probability? Here you see this is less equal to. So what should be the probability of this? This will always be what? What we can say? The probability of bigger than this delta is less equal to this epsilon L delta. And what can we say about the probability of that event? Like set of all sequences which satisfies that this probability of this event instead of this one complement of that. Okay, so what can we say about that event?
So 1 minus epsilon.
Yeah, so let's say this is star, okay. Then from star, then from star, we have probability of T. I'll use this later on, so that's why I'm just denoting it. Okay, and what is happening? Okay, let me. Oh, what is it? Okay, okay, okay. So I have this observation first of all. So what I am considering, see, we have to observe step by step. So here I consider all such sequences, okay, which we call uh, typical set of sequences which satisfies this one. Okay, the distance between or the difference between the self-information of UL and the entropy, okay, or the sample mean and the entropy is less equal to delta. If that is the case, then this is what we have. That probability of T is bigger equal to 1 minus epsilon delta, epsilon L delta. Epsilon is a function of L and delta. That's why I'm writing epsilon in bracket L and delta. And how this epsilon is related to our original sequence of source letters, UL bar. This is how it is related due to law of large numbers. Okay. Now, if that is the case, okay, then what we can write? Okay, here is one more thing. Let's say here, let's say double star. Now, from double star, from this, okay, this equation, double star, what can we write? Can I write that if this is mod of this is less equal to delta, then if we just relax the mod, what can we write? Huh? So what can we write about this? I UL bar by L minus HU. This would be less than equal to delta and bigger equal to minus delta. This is what we can write. So because mod of this is less than equal to delta, so it has to be in between minus delta to delta. And if that is the case, then what we can write? We can add both sides by HU. So we can write HU minus delta less equal to I UL bar by L less equal to HU plus delta. And so this implies I of UL bar is less equal to L times HU plus delta. Here L times HU minus delta. So that means, is that okay, this calculation? Is this calculation okay? Any doubt?
Yes, sir.
Okay. Now this is in terms of self-information. So, but self-information is nothing but from self-information, how do we define self-information? It is log of or minus time log of probability. So this is minus time log of probability of UL bar. If this is less equal to this is less equal to this. Now what can I say from here? This is L HU minus delta. From here, what can you say? Can I say probability of, okay, probability of UL bar, okay, this is less equal to 2 to the power minus L HU plus delta, and it is bigger equal to 2 to the power minus L HU plus delta. Can you say like this? I mean, this is a log base 2, okay?
So one side would be minus HOP minus delta.
What is that?
So right one should be minus.
Oh, both side. Okay, okay, okay. Yeah, you're correct, I think. Yeah, I think this one should be minus. Yeah. And this is very, very important. Why? Because if it is the typical set, Okay, if it is in the typical set, it means the probability of that sequence, okay, of any sequence actually in the typical set, the probability is lie between 2 to the power minus L times something, and it is bigger equal to the power this minus L this thing something. And this will play a very important role a little later. Okay, we'll say that, but let us see this. So now the question is, we started with only a set of sequences, which is called typical set of sequences of source letters, okay, which has this property, okay, whose probability sequence, I mean probability of each of these sequences between this and this, lying between this and this. If that is the case, okay, we also want to find out, let's say, how many such sequences could be there for which the probability will be lying between this to that. See, there are two things important here. One is we are connecting the probability of UL bar, probability of every sequence in terms of entropy. Okay, this is why it will play a big role later on. Okay, this is important. Now the thing is, if that is the case, this is the set of sequences we are interested in, which is called the typical set. Then we want to find out what is the size of the typical set. That means how many sequences are there of length L which will satisfy this. Okay, this is what we want to find out now. Okay, so now the next claim, our next question is, what is the size of the typical set? Typical set. That means what is the number of elements? Okay, that is what is the number of elements in T? This is the question. Okay, we want to find that. So we need to find a bound of this. That how many sequences are there? Okay, we have to find a bound. Okay, now let us find a bound. Okay, first of all, observe that probability of this T. Okay, this typical set. In fact, I mean, let us say, okay, here whenever we are saying that is entropy, okay, entropy, wherever we are writing, that means entropy is finite. Okay, this is already assumed. Okay, I mean, if you have a finite set of symbols, for example, in our case, okay, this is always finite. If you consider infinite set of symbols, then of course we have to also assume that this is finite. Okay, now PT, okay, this is if our symbol set is finite, or number of source letters, it is finite. The number of sequences is also finite. So how do you calculate probability of an event? If you know the probability of the elements, okay, are all possible outcomes. How do you calculate probability of an event? If you know probability of each individual outcome, how do you calculate probability of an event, which is a union of the possible outcomes?
So by taking addition of
Yes.
each.
Yes. So just by taking the sum, right? So let us take the sum. So probability of T, okay? This is again sum of, you can say probability of UL, okay? UL bar, let's say, for all UL bar, whatever it is, okay? Whatever it is, this is the case. Now, so probability of UL bar, all UL in this, and I do not know how many such sequences are there. So I do not know what is the number of such sequences. How many sequences are there in the typical set? So in order to find a bound, I can always say, let me just write it. Let me just write it that this is always less equal to mod of T. Mod of T means the number of elements in T times minimum of UL bar in T probability of UL bar. Can I say? Can I write it like this way? Okay, this is capital U, by the way. Can I write it? It is sum of this. So probability of UL bar, okay, is something. Okay, this is a number for all sequences. So there is a minimum number. So this sum has to be bigger or equal to minimum of this. But how many are these there? Mod of T are there. You got it? PUL, let's say PUL bar. It is of course bigger or equal to minimum of UL bar for all UL bar in T. PL PUL bar is always bigger or equal to minimum of all those. Right? And how many are those? They are in the summation. This is T many. I mean mod of T many. The number of sequences in the type set, a typical set, or sometimes it's also called type set, by the way. So let us call it typical set here. So this is always equal to this. Is there any doubt about it? Is there any doubt here? This follows from the fact, okay, since, let me write it here, since probability of UL bar is bigger or equal to minimum of UL bar probability of UL bar. Simple. Does anybody have any doubt about this? Hmm? Any question about this? Are you guys sleeping or what?
No, sir. No, it's fine.
It's fine? Okay, okay, good. So now, now this is a probability, right? So this is also less equal to 1. So from this, what can I find out? From this, what does it imply? That mod T times minimum of PUL bar over all UL bar T. This is less equal to 1. So it implies mod of T is less equal to 1 by, let's say, minimum of UL bar T, UL bar in T, and P of UL bar. What is probability of UL bar? This has a bound. Here we developed. This is, let's say, star, star, star. And this is 1 by this. So what can we say? What should be the bound here? I can use that because it is in the denominator. So 1 by this. I should use the lower bound of this, which is 2 to the power minus L this. So now since let's say P of UL bar is bigger or equal to, what was that? 2 to the power minus L HU plus delta. 2 to the power minus L HU plus delta. Okay. For all UL. So minimum will also be bigger or equal to this number. Okay, there is no doubt about that. Because probability of this, the minimum of this also should be this. So this is bigger or equal to this. So 1 by this is what? So 1 by this, which implies 1 by P of UL bar. Okay. This is less equal to what? 2 to the power. So this will go here. Will go 1 by this 2 to the power L HU plus delta. So this is the case. Okay. So this implies then what? Mod of T is less equal to 2 to the power L HU plus delta. Is that okay? So
Yes,
number of
sir.
this, yeah, number of the sequences, I mean, number of elements of this sequences is less equal to this number. Whatever be this number, less equal to this number. Okay. Here I'll give you homework. Okay. The homework will be homework. Everything is there in that book, Thomas and Thomas, but in a different way. Okay. The find an upper bound for mod t. Okay. Find upper bound for mod t. In fact, show that mod t will be less equal to. Oh, here I got already the upper bound. We have to read the lower bound. Yeah. So we have to read the lower bound. Yeah. Uh, lower bound. Okay. And lower bound of this. So we have to you have to show, this is very simple, by the way. Okay. That this is bigger equal to 1 minus, I'll give you a hint also, maybe delta times 2 to the power L HU minus delta. So can anybody tell me how to find this lower bound? Can anybody tell me? How did I found the upper bound? See, using this is a crucial step here. How can I find the lower bound? Okay, the hint is instead of mean, you can use max, and this greater equal to sign will be less equal to in that case, and then you can derive the bound. Okay, so that's the hint. Okay, and this is very, very important, by the way. Okay, that number of this typical the elements of the summer sequence, the typical set. Typical set means what? The difference. Okay, the difference is here. The difference is less equal to lambda at delta. This is the typical set. Okay, the UL is something. So the entropy and this sample mean, okay, or the, let's say, the average self information, okay, is like this. Okay. Okay. So now finally, so we got what? We got a sequence of this. Okay. So we said we'll fix a sequence. Will not consider all possible sequences of the source letters of some particular length L. In fact, we'll consider a typical set of sequences, which is this. And we found that number of these sequences in the typical set is bounded above and below by these numbers. Okay. Bounded above by this, bounded below this. And not only that, probability of each sequence in the typical set is bounded above and below by this equation 3 star. Okay, probability of each sequence, okay, in the typical set. So here UL bar is in T. Typical set is lying between these two. Now let us focus on our original question. Okay, the original question is what? How to construct this number n. Okay, let us go back to our original question. Now we'll answer the original question. So question is, okay, how to decide what is the fixed, what is the value of n, that is the fixed length, the length of, or the fixed length of all code words. Okay, this was our original question. Okay. Okay. First of all, we'll now introduce the probability of error here. Okay. So first of all, we'll consider two cases. first, let us choose n which satisfies n log d is bigger equal to L HU plus delta. Okay, why we are choosing this number? Because I know the proof of this Shannon. But why Shannon? How did Shannon had this guess? Because maybe he, in order to prove his ultimate theorem, he has observed something and maybe he did little bit of back calculation. I don't know. Okay, but since I know the proof, so that's why I'm choosing that. Okay, let us choose n to be this. Otherwise, you can choose n to be less equal to this. There may be two cases, but this thing is important, which is playing roles in every bit of pieces here. You see, L times HU plus delta, L times HU plus delta or minus delta. Okay, this is playing a big role in all of this results. Okay, so let us first choose that n log d is bigger equal to this. Okay, then what you can show? Now see here, we have proved mod of t is less equal to this. So this is my, let's say, fourth star. Mod of this is less equal, mod of t is less equal to 2 to the power this. Okay, 2 to the power L H U plus delta. Okay, so if this is the case, n is, so here you can assume that log n is log base 2 d. Then what can I assume? What can I have if I choose this? So if you do a little bit of calculation, what can we have? D to the power n should be bigger equal to 2 to the power L HU plus delta, right? This is log base 2. So this thing is equal to log of 2 d to the power n, which is bigger equal to L HU plus delta. Okay, so that is d to the power n should be bigger equal to 2 L, okay, HU plus delta. But this is exactly the number of what? This typical sequences, typical set is bounded above by this number. So number of typical sequences is less equal to this, right? So which is number of, or maybe here directly you can write from here. This implies d to the power n is large or bigger than or larger than the number of sequences in the typical set T. Okay, so therefore if n is larger than this means what? A separate code word can be, if n is the, let's say whatever be n, let's say if you choose n this way, this is the way if you choose. Okay, see everything here is known, by the way. Delta is fixed because unless you have delta, you cannot define your typical set. Each of you, this entropy is fixed because you don't know this, the probability distribution of the symbols, the source letters. L you already know that what is the length of sequence. D you already know, okay, and N is the desired thing. So you suppose you set N to satisfy this one, then it automatically implies that separate code words are possible. Separate code words are possible for all the sequences in the typical set, okay? Because 3 to the power n is larger than that, the number of sequences or number of elements of the typical set. The separate code word is possible for each element UL, let's say, which is in T, typical set, okay? Now, if that is the case, then what can we say about the probability of the error? Can I say, okay, before that, let's say, do you understand what I'm saying, guys?
Yes, sir.
Yes, sir.
Okay, okay. So because there is a silence, so I'm just thinking, okay, no problem. Now, if this is the case, now can anybody tell me what should be the probability of error? Now, what is the meaning of probability of error? Probability of error. That means there is a code word, okay, for which the original sequence, original, or there is a sequence of code words for which the original sequence of source letters, okay, is, let's say, not possible, okay? It's not possible to derive, not possible to derive. Okay, so probability of error. Let me denote it by probability of error is denote it as PE. Now, what can you say about probability of error if this happens? If n is chosen like this, what can you say about probability of this error? The probability of error is what? There is almost no probability of error, right? Because every sequence, every sequence in the typical set has a separate word. But, okay, but what is the meaning of saying sequence is in the sequence in the typical set? This is how we defined it here. Here, how we defined it. This is less equal to this, which means we have, yeah, we define typical set, which means that this probability of I UL bar by L minus HU is bigger than delta. If this is the case, the probability of this is less equal to epsilon L delta. Then we define typical set as that the difference between these two is bigger than equal to delta. Sorry, less equal to delta. Okay, less equal to delta. Okay, then what can you say about the probability of error? Any idea? See, probability of error definitely will depend on delta, right? Why? Because our typical set is defined in terms of delta. The distance is less equal to delta. The distance between the self-information of UL divided by L and the entropy of this. So what can you say about the probability of error? Can I give you a bound? Mhm. Guys, can you give a bound here? Look at this equation. Look at this equation, or you can see it here. Okay, so for the time being, let us say we don't know this. Okay, let us assume like that. We have to find it. We'll come back to this again. Okay, now, okay, so now assume otherwise. Otherwise means if, okay, so let me call it a homework, but we'll discuss this next week also. So if this is not assumed, otherwise means if this thing is not assumed, then what will happen? If this is not assumed, then n log d, okay, n base 2, let's say log is base 2, is less equal to L or less than L times h of u plus delta, right? Is that okay?
Yes, sir.
Okay. But instead of that, let us assume, because again, I know the proof, so that's why. So let us assume that n, otherwise let, we'll come back to these logics, but let us say let n times log of d is less equal to L HU minus 2 delta. Okay, there is a reason for this. We'll come back to this. Okay, why we are assuming this. Let us choose that this is, in fact, when we choose this one, we'll show that when L goes to infinity, this probability of error will go to 0. Okay, and now if this is chosen, like n log d is less equal to d, if this is chosen, then we'll see what will happen. Then what will happen? Then d to the power n, okay, is less equal to 2 to the power L using the same calculation which you did 2 delta. Okay. Now here the interesting thing is, if this is the case, now what is the probability of UL bar? Okay, when, so here you see probability of this. Yeah, probability of UL bar, okay, is less equal to 2 to the power minus L HU minus delta. Okay, from the C, this equation 3 star. So if we use that, then what will happen is, now from this star star star, okay, from this probability will bar, this is less equal to 2 to the power minus L HU minus delta. Okay, then this is, from this we have this, and d to the power n is less than or equal to this. Then what can we say about the overall probability of all the sequences in the typical set? That means what I'm trying to tell you is, what is the probability that we can provide separate code word for each of the elements of the typical set? Question is, using this inequality, Question is, what is the overall probability? What is the probability that we can provide separate code word for elements in the typical set? Number of sequences here, dn, okay, coded, could be at most 2 to the power this. And probability of ul bar is equal to this. So what can we say? That means this probability of ul bar means what? This probability, this ul can occur with this probability. Okay, the probability which is upper bounded by 2 to the power minus l this. And how many code words are there? Number of code words is 2 to the power l hu minus 2 delta. So what is the number of, what is the overall probability? How many you can provide? This will occur with probability this ul, each of this. So what is the probability that you will able to provide a separate code word? This probability times this probability. Because you understand what I'm saying?
No, sir. Please repeat.
Yeah. So this probability of UL bar means what? This probability UL will occur with this probability, right? This is what the meaning of probability of UL bar, right? UL is a sequence of length L of source letters. So with probability this one, which is less equal to this value, yeah, from here. Now dn is less equal to 2 to the power this. That dn means what? The number of sequences of length n. Okay, sequences of what? Sequence of the code letters, because they are from the set d. Okay, they are from the set d is less equal to this. Now for each of this code word, okay, and one particular, so these many code words are possible. You have this many code words. Okay, you can generate this many code words. This is l. Okay, this many code words are possible. Okay, of length n. Now, EL is in the sequence of typical, which is in the typical set. EL bar is a sequence of source letters, which is in the typical set. Now, what are you trying to say? How many, what is the probability that you can give a separate code word for each of these elements in the typical set? There is a question. This can occur, EL bar can occur with this probability, at most this probability. So what is the at most probability that this UL, okay, will take one of this DN, sequence of DN. I mean, yeah, so DN is the number of total sequences. So what is the probability that it will take one code word from that? So it is this times this number at most. Okay, let me explain it a different way. So you have 10 beans, let's say 10 beans, okay, but anyway, 10 beans, okay, and you have, so 10 beans are like this possible number of this, so code words, okay, code words. Now there are, let's say, 10 balls, or maybe the number of balls I don't know, but I know that there is a set of balls. A set means here is the typical set where probability of occurrence of each of these elements of the set, okay, is known to me. Now the question is, what is the probability at most? At most is given, not a precise probability is given, at most is given. The question is, what is the at most probability that an element of this set will be in one of the bins? You understand my question?
Yes, sir.
So this will be this probability at most, this probability times that probability, that number, d to the power n is bounded by that number, isn't it? Okay, we'll discuss this next day. So let me write down the question here. What is, yeah, what is the at most here, huh? Probability that, okay, that the elements of, did I write this there? Yeah, I already have written it. Okay, so there is no point to write it. Yeah, this is the question which you want to address next day. This one, as well as the question on the top. What is the error? Can I give you a bound? Can I give a bound for this error probability? Okay. Yeah, does anybody have any other question? No. Okay. Okay, guys, by the way, so this Saturday, okay, there will be no class in